So we're going to start looking at the graphs of polynomials. And in particular, what I want us to focus on early in this section is understanding what happens when a graph of a polynomial hits the x-axis. And these three graphs are kind of a nice emblem of what you're going to see when you look at the behavior of a polynomial function near a root. Now, polynomial functions are typically written like this: an x to the n plus an minus 1 x to the n minus 1 plus all the way down to a2 x squared plus a1 x plus a sub 0. Anything in this form is a polynomial function. So we want to understand what dictates the shape of these things, etc. Now, the link that I gave you on Desmos or on D2L to our Desmos link should give you something like this. When you have even degree polynomials, then you get similar behavior. The graph touches here at x equals 0 and y equals 0. Same thing with this next graph. Same thing with this graph. What's happening here on the x-axis is that as your degree gets bigger, it gets flatter between -1 and 1, but then gets taller quicker once you leave that range. So there's your even valued polynomials, or even degree polynomials. Yeah?
Do they all meet at -1 and 1? Do they all?
Yeah, they all cross at -1 and 1. So all three of these are going to cross right there. In fact, if I wanted to, I could do another one. Let's do x to the 8th. X to the 8th is going to be even flatter, but it's still going to cross at -1 and 1. But notice that x to the 8th gets even taller, even faster. So they grow very, very quickly. Hannah?
So these are always going to, and this even number is always going to meet at 1 negative.
Yes. Yes. Now, that's not the part that I want you to focus on. I want you to focus on the behavior of the graph at x equals 0. And it's best seen with the smallest of these, y equals x squared. So with y equals x squared, you can see it pretty nicely. You've got a vertex here, and the graph's going to kind of bounce off the x-axis. So that's one of three different behaviors that we're going to see here, is that you can get a bounce. So let's add that to our graphs, or excuse me, add that to the back side of our handout. For even degrees polynomials, the behavior of the root at x equals 0 is to bounce. And then there is a little typo on this. This should say odd degrees. My bad. Now, by even degree, I mean things like 2, 4, 6, 8, etc. For odd degree, I'm not going to include 1. 1 is going to be a special case by itself. But there will be some odd numbers other than 1. 3, 5, 7, 9, etc. Yeah, you've got it. So those are your odd degrees. Let's see if we can't figure out what's happening with the behavior of our polynomial at those points. So I'll shut this one off. Let's turn these on. And here's where I introduce a new kind of really pseudoscientific term, and that's a wiggle. These graphs aren't going straight through. They're not bouncing. They're kind of snaking their way through. But wiggle sounds a little bit more fun, a little bit more user-friendly, so we're going to go with that. So we've got a couple different types of behaviors. This one's going to be a bounce. This one's a wiggle. And this last one, we're going to characterize as exactly what it is. It just goes straight through. So those are your three behaviors. Now, in general, they're going to happen exactly when you have different exponents for this x. So you've got bounce, wiggle, and straight through. And And what's nice about this is that with this understanding that for even degree polynomials, or excuse me, even degree roots, you're going to get a bounce, or with odd degree roots, you're going to get a wiggle. You can really predict what a function is going to look like. Now we're going to have to couple that up with one more thing here, and that's going to be yet another handout. That's going to be your end behavior of that polynomial. So let's take a look at that for a moment. So your end behavior is going to depend on the degree of the polynomial. So you're either going to have an even degree or an odd degree. If you have an even degree, you can think of like a polynomial, like x squared or x to the fourth. Eventually, that graph's going to point up to the right and up to the left. So like this. Now that's assuming that the leading coefficient is positive. So that is an important assumption in this. The leading coefficient is positive. What if the leading coefficient is negative? Well, then you're going to have kind of the opposite behavior. Both arms of this are going to point down. Now, what happens in between there? You've got this dashed line. Could be a lot of things. We're going to figure out what happens in between. But what we're going to look at is the end behavior. Eventually, these graphs are going to have to look like one of those two if they have an even degree leading exponent. What if they have an odd degree? Well, that's over here. Odd degree is going to go down to the left and up to the right, assuming that you have a positive leading coefficient. That gets flipped around if you have a negative leading coefficient. Now, just a quick FYI, when you look at this stuff on WebAssign, they use this notation. And let me kind of zoom in on that a little bit. They say, all right, as x approaches infinity, what happens to the y coordinate? Well, as you approach infinity, in the x direction, the y coordinate's going up and up and up. So it's going to infinity. If you approach negative infinity, then what's happening to the y coordinate here? It's approaching negative infinity. So that's the notation here. It's kind of a foreshadow of stuff you're going to see in calculus. Let's move over to here. As x approaches negative infinity, the y value is getting taller. So y value is approaching positive infinity. And same thing over here. X approaches infinity, y approaches infinity. So just some notation to be aware of. But we're going to use that notation, or not that notation so much, but we're going to use these ideas to try and figure out some things about our polynomials and what their graphs are going to look like. So let's keep this in mind. Let me number this way: A, B, C, and D, so that I can refer back to these different behaviors. Say, well, which behavior is it? And you can just call out a letter. And let's start using this to try and make predictions of some of the behavior of our polynomials. Now, the way it's going to work is we're going to look at our polynomials, starting with this one right here. Y equals x plus 2 cubed times x minus 2. Now I want to look at a couple of these terms and figure out, well, where does this actually equal 0 first? So can we eyeball that? Take a look at this first binomial. Where does that actually equal 0? Negative 2. So I've got a root at negative 2. How about the second one? Positive 2. Now there's something there called multiplicity. Let me help you understand what that is by thinking of it this way, or taking a look at it this way. If I'm solving x plus 2 cubed times x minus 2 equals 0, because this is cubed, I could think of that as x plus 2 times x plus 2 times x plus 2 times x minus 2. So where does this actually equal 0? Well, x could equal negative 2, or x could equal negative 2, or x could equal negative 2. And one last one, x could equal 2. But this occurs as a root 3 times. And that's what we call the multiplicity. How many times does it occur as a root? Well, it occurs as a root with multiplicity 3. How about x equal 2? What's the multiplicity of that root? 1. Thank you, Nick. 1. Okay. What's the behavior of a function that has a multiplicity of 3 for its root? Well, we go back to flip side of our handout. Actually, don't even go to the flip side. It's right up here. If you have an odd degree, then this function should have a wiggle. That's the behavior of the function at that root. How about the next one? At x equal 2. What's the behavior going to be there? Somebody said it? Straight through. Thank you. Straight through. Now there's something convenient that kind of happens here that helps guide ourselves a little bit. If you add up the multiplicities, we get 4, but that 4 happens to be the degree. If I multiply this polynomial out, and I don't really want to because right now it's nicely factored, I can see where the roots are, and it tells me a lot about this polynomial. But I could multiply it out and get degree 4. Which of my behaviors do you think I'm likely to see for the graph of this polynomial? A, B, C, or D?
C.
Got a couple votes for C. I like that. All right, it's going to have an even degree, so it has to be one of these. And because these are all positive terms in terms of the x, when you multiply that out, it's going to be, it's going to have a positive leading coefficient. So its end behavior equals C. Okay, good. Let's do one last thing to help ourselves graph this, and that is let's find the y-intercept. How do I find the y-intercept of this graph? Ryan?
Set it to 0.
So I just thought I'd throw out Ryan, that way one of you would answer. I figured I had a better chance there. Okay, so Ryan, what do you do to find the y-intercept? The silence is oppressive from Ryan. So we set x equal to 0. Can anyone do that in their head? If you set x equal to 0, what are you going to get? Two cubed is 8 times negative 2 is negative 16. So your y-intercept should be at 0, negative 16. Let's put that on our graph. So 0, negative 16, it's about down here. There's a couple other points I can put on my graph. One of them is here, and the other one is here. Now, eventually, we know that the graph of this is going to go up to the right and up to the left. So, it's going to look something like this here and here. Do you think I'm going to take your graphing calculators away from you on the exam? No. There is nothing wrong with looking at this at your graphing calculator. But you should be able to predict what's going to happen when you come at this. Sabira, you had a question?
Where did you get the degree from?
By adding up the multiplicities. If you multiply this out, I'd have an x cubed term times an x cubed times x, that would be an x to the fourth term. Now, expanding this out, you're going to get something much different than x cubed plus 8. It's going to be x cubed plus 2x squared plus 4x plus 8 if you cube this all out. Now, the tricks in that are going to be the last thing we cover in this course, so it's going to be a while before we get there. But if I multiply an x cubed term times an x term, that's where I get x to the fourth. Or you could look at it this way. This has degree 3, this has degree 1, add them up, you get 4.
Yeah, that's easier.
Yeah.
What about end behavior?
So the end behavior comes from two things. That's going to be the degree of your polynomial, which is even, so we can ignore these two cases, and you've got a positive leading coefficient, so it has to be case C. If it had a negative in front, then it'd be case D. We also know the behavior of the function at these points. So let me kind of freestyle this. I know a few things about my graph. I know that as this comes into this point, it's going to wiggle through. And for your convenience, I put a point down here already, and that's at negative 20 something, where you have a minimum. So that's what the graph has to look like, at least part of this graph. Now the rest of this is going to come up. What's this function going to do when it touches the x-axis here?
Wiggle?
It's going to go straight through.
It's going to go straight through. So let me just go straight through. And there's the rest of our graph. Now, like I said, you can confirm this stuff on your graphing calculator, on Desmos, whatever tech you have available to yourself. But the things that I'll be looking for when I grade your problems is, does it have the right behavior here and here? Well, not so much here. But at that point, it's nice if you have that one correct. 0, negative 16. But this one's got a wiggle. And this one is straight through. That's what I'll be looking for.
I have a question then.
Please.
So the end behavior, you said that if it's positive,
If it has a positive leading coefficient.
a positive leading coefficient, how do you know this has a positive leading coefficient?
Well, I didn't really multiply it all out, but you can kind of look at the terms here. You've got x plus 2 times x plus 2 times x plus 2 times x minus 2. The leading term is going to be the x times the x times the x times the x. Those are all positive, so you're going to get a x to the fourth term. And even though it's not written, it's understood that there's a 1 out in front. So it would have to have a positive term. Now the rest of these terms, who knows? And actually, it doesn't matter what those terms are. The end behavior is going to be the same. So let me illustrate that part of it with, kind of getting ahead here a little bit. No, let's see, is it on this graph? Yeah, I think it's on the back side of this. Or is it? No, it's on the back side of our end behavior graph. Let's take a look at two different polynomials. So we'll look at p of x, which is this one in orange. And then I'll look at q of x, which is this one in yellow. Now here, I don't have this all factored, so the way I judge the degree is just by looking at the highest degree term. So I don't add the exponents here and go 3 plus 2 plus 1. You're just going to look and say, all right, the degree here is 3. The degree here is 3.
It doesn't matter how complicated the numbers look, as long as the leading coefficient is
Negative.
negative or positive.
Yeah, or positive.
And the degree is odd or even.
Right, so which of our behaviors is that going to be? A, B, C, or D?
See?
Got to vote for Brandon? B?
Thinking D.
Well, what's the degree of this polynomial?
3.
3, and 3 is odd, so it has to be one of these. And the leading coefficient's negative, so, okay, leading coefficient's negative, it has to be B. So eventually, these graphs are going to look like this. And in fact, you can take a couple different looks at this by graphing it. So let's take a quick look at that. Let me get rid of the stuff that I have here. And I'm just going to do negative x cubed. Then you got to hit the right arrow divided by 8 plus 1/4 x squared. So for the 1/4, I'm just going to type in 0.25. You know, you can type in x squared divided by 4 or 1/4 x squared as you see fit, plus 12x. Well, that's one graph. Let's graph the other one, or let's plug in the other one. Negative x cubed divided by 8. Now these look a lot different in terms of the functions, but their graphs are eventually going to be pretty close to each other. Now I'm going to modify the window that I have there for you. I'm going to start by graphing it from, say, negative 6 to 6. And now I'll go with negative 75 to 75. Let's see what that does for our graph. So if you want to come up with the same settings, there they are. Wow, these graphs look nothing alike, do they? They look pretty different. But what I say is that as the farther and farther away I get from x equals 0, the farther away I get from the x-axis, the more these graphs are going to look similar. So let's try and do, say, negative 25 to 25 on the x-axis. Negative 25 to 25. And I'm going to make x scale equal to 5 here. On the y-axis, let me go from, say, negative 300. I'll do negative 350 to 350. And now let's take a look at these graphs. I probably should have changed y scale, made it something a little bit bigger, like 25 or 50. And they're starting to look similar, all right? And the farther out I go, the more similar those graphs are going to look. So if I go out from like negative 35 to 35, and I'm going to cheat on this one a little bit, I'm just going to use zoom 0. Is there much difference between those graphs? In fact, to the left of x equals 0, it's tough to tell which one is which. So, all right. Now, for those of you with a nice color graphing calculator, you can see that the blue graph to the right of the x-axis is the taller one. So I'll do that one in orange on my handout. So that's the taller one. And to the left of the y-axis, these two graphs look pretty much the same. So yeah, the right of the y-axis, you can see a little bit of a difference there, but not much. So, and that's the whole point, is that eventually this polynomial is going to look like this because these smaller order terms just don't mean much. They're not going to help determine the shape of the graph that much for very large values of x.
Like the what terms won't,
Say again?
what terms won't determine?
Oh, these terms. Notice that, you know, these two things are the same. Those two things are the same, and they have more or less the same graph. So it's these leading terms that really determine the behavior of the polynomial. So when you're close to x equals 0, these terms will make a big difference. But when you're far away from x equals 0, not so much. Okay. Let's see. Let's take a look at this next one. So we have the same two roots in this one that we did with the last one. What are our two roots? Well, -2 and 2. Are you comfortable yet with the multiplicity? Can you read off the multiplicity of each root here? 2 and 2. Good. The multiplicity is just this term right here. It's how much, it's, you know, what degree each of these binomials is raised to. So the first one's a 2, the second one's a 2. They don't have to be the same as are in this particular example. 2 and 2. Okay. What kind of behavior do you expect when you have a root at 2, or excuse me, a root with a multiplicity of 2? A bounce. And another bounce. So bounce for both of those. Let's do what we did with the last one. First of all, determine the degree. Amber, what's our degree here?
4.
4, nice. So what end behavior does that give us? Which one do you expect here?
C.
Yeah, I like C. You've got an even degree, so it has to be one of the orange graphs here. And because everything's going to be positive when we multiply it out, at least in terms of the leading coefficients, it's going to be have an end behavior of C. Let's determine the y-intercept. Caitlin, how do I determine the y-intercept?
You put in 0 for x.
Can you do that in your head?
It's 16.
Yes. So if you put in a 0, you get 2 squared, which is 4, -2 squared, which is also 4. 4 times 4 is 16. And that point is already here for you on your graph. Thank you. Let's put in our x-intercepts. Those are going to be halfway between, you know, the -5 and, actually not quite halfway. So 2 here and 2 there. I know the eventual end term behavior of this graph. It's going to come up to the left and up to the right. That's eventually what this graph is going to have to do. As far as what happens in between, well, I'm going to get a bounce here. It's going to bounce up, touch the y-axis at 16. And when it comes down, what kind of behavior am I going to get at this root?
Bounce.
Yeah, another bounce. Another bounce. And then like that. Now, in truth, the graph would look a little bit more symmetric than what I've drawn. In fact, it would be exactly symmetric because it's an even function. But that's a property we haven't gone over yet, so not worried about that. There's your graph. Now you can double check those things on Desmos or on your graphing calculator, It should look like a nice even function. Let's kind of scroll down a little bit. I think I have that one. Maybe I don't. All right, so easy enough to put in. Y equals x plus 2 squared and x minus 2 squared. So there's our graph. Looks pretty much like what we said it would, right? And you've got that y-intercept here at 0, 16. Great. So it's really helpful if you have these things factored. And that's going to be something we'll circle back and look at. Are we okay with this graph?
I have a question.
Yes.
I think what's confusing about the degree is that I forgot what math concept it was, but there's another math concept where the degree is the highest power.
It is still the highest power. So the highest power of x that you see in this polynomial is 3, right? Same thing here. So that's your degree. Now, we don't really see an x to the 4th power here, but you've got to realize that this is factored. If you multiply this out, this term would have an x squared, this term would have an x squared, and when you multiply an x squared times an x squared, you'd have an x to the 4th.
Okay, I get it.
So it is still the same thing that you're used to. It's just that because your instructor is really charming and considerate, he already factored these things for you. All right, cool. Appreciate the question. Let's take a look at this one. This is kind of a nice one. If you're following me along on Desmos, you can kind of really play along. Let's parse through this and understand a few things. So first of all, let's take a look at the roots, and then the multiplicity, and then the behavior at those roots. So let's start here at the leftmost of this product. Try and list off each of the roots. And the roots are exactly what you think. You're going to be setting this polynomial p of x equal to 0. So negative of x plus 1 squared times x minus 1 cubed times x minus 2. And when you set this equal to 0, you really got to look, well, where is each term equal to 0? So, Kyrene, what would make the first term equal to 0?
-1.
Good. Second term?
+1.
And the last one?
+2.
Perfect. Perfect. Oz, what's the multiplicity of each of these terms? For like x equal 2.
Can you call somebody?
Sure. Lucas.
For the first one, I'd do 2, and then 3, and then 1.
Good. 2, and then 3, and then 1. Now the multiplicity is just going to come from the exponent of these binomial terms. So 2, 3, and even though it wasn't written, Lucas correctly assumed that the last one is a 1. All right, nice. So Ryan C., if a polynomial has a root at -1 with a multiplicity of 2, what kind of behavior am I going to expect at this one? A bounce, a wiggle, or straight through? Yeah, that one should bounce. What should the next one do? Amber?
Wiggle.
Wiggle? Good. And how about the last one? Ryan G?
Straight through.
Straight through. Nice. So you kind of know what to expect from those things. There's one last thing that we should probably pay attention to, and that is the degree of this polynomial. Overall, Angel, what's the degree of this polynomial? Yeah. The degree is 6. So if I have a degree of 6, I need to determine the end behavior. which end behavior am I going to get if I have a degree of 6? Yeah, let me. Yeah, so it's going to be D. There we go. D. I shouldn't have written on the back of this one. Darn it. All right, so it's going to be D. End behavior is D. So that means exactly what I have drawn here, that eventually this graph is going to come down to the left and down to the right. That's our end behavior. In between, we've got a lot of things happening. For instance, we've got a root at -1. So that's going to be up here. I've got another root at +1. And then a root at 2. So we got to make these roots behave like their multiplicity tells us. So if you're following along on Desmos, then it's kind of a little bit fun. Let me shut off. Let's shut off this one. Yeah, please.
It's D because the first term is negative, right?
Correct. So I appreciate you helping me or remind me to highlight the fact that you got a negative out in front of this polynomial. So although we had an even degree, we had a negative leading coefficient. That's why this one was D and not C. So yeah, good job. So let's go back here. You can graph each of these. So that's the end behavior here. So got the end behavior. And then what we expect? We expect this first polynomial or the first part of the polynomial is supposed to bounce off the graph at -1. And there's your bounce. So we can sketch that part in. Let's do that. And then if you're on Desmos, you can click these other two. Now, if you notice, I've got a little bit of help for you on the graphs, that it passes through these points. This is your y-intercept. That's maybe something you should be able to determine. The y-intercept on this one is going to be a -4, just by setting x equal to 0. But what's going to happen to the graph when I get to this point? Yeah, you're going to have a wiggle through. Now, the scale on this one is not perfect, so let's see. Let's just take a look at it first before I draw it. But it is going to be a wiggle through. Wrong one. How about this one? There you go. So there's your wiggle through. It doesn't just go straight through. It kind of hesitates a little bit. Says, I might change my mind. No, I won't. And then finally, we got this last one where it's going to go straight through. Let me kind of zoom in a little bit so we can see a little bit more exaggerated that it doesn't just go straight through. The next one's going to go straight through, and I hope that you see the difference. So there's your straight through. Notice that it doesn't, play along the x-axis for a little bit. It doesn't bounce off the x-axis. It just literally goes straight through. So there's our last piece. And I'll draw that one here. And apologize for the vertigo. So there's your graph. Nice. How are we looking on that one? Doing okay? Let's turn our attention to some of the homework problems then. So this is kind of like the warm-up. Now we're going to look at some of the homework problems. And the first one I want you to look at is this one, example A. And I want you to determine for yourself which of the 4 behaviors you think you're going to see based on this graph. And from the 4 behaviors, I'm really thinking of these choices. Which of the 4 am I going to get when I look at the graph of y equals ax cubed minus 7x plus 19? Now, I deliberately didn't give you the value of a, since you can't just plug it in your graphing calculator. I want you to think about it. Hi.
Did you pass those out in the beginning?
I did. Help yourself.
All right. Not see up there. Thank you. Yep.
So, which graph do you think fits? Which one do you think this is going to look like?
A.
Okay, got a couple votes for A. Anyone for B? Could it be B?
Yeah,
Sure.
if A is negative.
So it kind of depends.
Wait.
It's going to be A if little a is greater than 0. It's going to be B if little a is less than 0. So it depends on, the sign of that leading coefficient. It could be one of those 2 possibilities. You just don't know. You got to kind of, be a little bit careful in how you play that one. Now, let's move down to example B here. Are we okay with this one? Doing okay? All right. So for example B, I'm going to extend this a little bit. We've got y, or q of x equals negative x squared times x squared minus 4. I could also write that as negative x squared, and that middle term is going to factor. X minus 2 times x plus 2. So let's just remind ourselves of a couple things here. The roots here would be what? What are my roots?
0, 2, 2.
Nice. X equals 0, x equal 2, x equal negative 2. And now let's throw in the multiplicity.
Bless you. Gesundheit.
Thank you. Danke. What about the multiplicity of x equal 2 or x equal negative 2? What's those multiplicities? 1 and 1. So you have a total of 4 here. What's that 4 telling me? What do I need that 4 for? The degree. So Sabira, I didn't need to do it this way. I just did it that way for the practice. But if you look here, if you distribute a negative x squared times x squared, that's going to give you a negative x to the 4th. And that negative x to the 4th would be your, your leading term. So negative x to the 4th plus 4x squared. Your degree is 4. So you can do your degree in a couple ways. You can add up the roots and their multiplicities, or you can look at the highest power. Both of them give you the same information. Now, what end behavior does that reflect? Yeah, got a couple votes for D. It's an even term, or even degree, with a negative leading coefficient. So end behavior is going to be D. And behavior equals D. Now, as far as the rest of this is concerned, there is a couple things that WebAssign might ask you to fill in. And that's going to come from our end behavior graphs. oops, other way. As x approaches infinity, what's happening to the y-coordinate? Where is it going? To negative infinity. And as x approaches negative infinity, the y-coordinate also approaches negative infinity. Now that could change depending on which of these four end behaviors you have, but for this particular one, they're just asking you, well, where does the y-coordinate go? And the y-coordinate in this case is going towards negative infinity, and same thing here. You know, it should say a little bit more. I'm kind of unhappy. It should say as x goes to infinity, or as x goes to negative infinity. So it probably should say that out in front. So that way it kind of looks like what the end behavior is on our handouts. You know, as x goes to negative infinity, y goes to positive infinity, that kind of thing. So, yeah, maybe you want to add that into your notes. Let's try one more end behavior kind of problem. That's example C. Which of the four end behaviors does this one have? Well, again, you've got to determine what's the degree here. And does it have a positive or negative leading coefficient? By the way, you can't cube this out and go, all right, that's x to the 6 minus 125. That's not true. Like I said, the way you have to do that is a trick that we're going to learn at the end of the course. For now, just think of it as x squared minus 5 times x squared minus 5 times x squared minus 5. If you looked at the leading coefficients, the leading terms here, x squared times x squared times x squared, what's that going to give you?
X to the 6.
Yeah, it's going to be y equals x to the 6 plus something. And it really doesn't matter what that something is. We don't have to multiply it all out. So there's two things that I need, and I've got them both. What's the coefficient understood to be in front of the x to the 6th?
1.
A 1, which is positive. And your degree is even. So what behavior is that?
C.
Yeah, end behavior C. So, end behavior equals C. Yay. All right. Bless you.
Plus,
Let's look at this one. Are we okay with C before I move on to D? Got some nods there? Thumbs up? All right. Let's look at D. First of all, let's determine the end behavior. What end behavior do you expect on this one? Annie, maybe you can help me out. What degree polynomial would this be if I multiplied it all out?
4.
Yeah, it'd be degree 4. And what's the leading coefficient going to be? Positive or negative? Negative. Because you do the multiplying out first, you'll get an x to the 4th term, and then you'll distribute the negative. So good job. So which end behavior is that for us?
D.
D. So this is going to have an end behavior D. And unfortunately, that doesn't really eliminate any possibilities here for us, does it? No, it doesn't, which is a bummer. How about something else? Can anyone tell me anything else about this polynomial? Hannah?
You possibly read it saying that x plus 4 be the left 4.
Yeah, so it's going to have a root at negative 4. So root at negative 4. Does that help me out? Yeah, because we can eliminate this one. This one has a root at 4. Root at x equal 4. Well, put a little frowny face there. That's not what we wanted. How about this third graph? What's wrong with that one? How many roots does this have? Has 2 roots, right? Our polynomial is only going to have 1 root. So has 2 roots, neither of which is at 4. Actually, pardon me, neither of which is negative 4. So, all right, that's kind of a bummer. But this one, that one's our Goldilocks, right? That was just right. You've got a root at negative 4, so that looks good. X equals negative 4, and it opens down. Now, we can't really see it, but if you took and plugged in x equals 0, 4 to the 4th power is 256. Negative 256, that's where this would cross the y-axis. Well, it looks possible. I mean, it's heading down there, so you can feel good about that one. Let's flip it over to the back side. We've got 4 graphs here. I want you to start by eliminating 2 of these. Which 2 can this not be? Without taking out your graphing calculator. You don't need your graphing calculator. That's overkill. So let me number these. Yeah. This one. 1, 2, 3, and 4. And let's see, we're gonna eliminate graphs blank and blank because which 2 graphs can I eliminate and why? Yes?
1 and 4, because those would need a positive coefficient.
Exactly. 1 and 4. This has the wrong end behavior. This would reflect an odd degree polynomial with a positive leading coefficient. We've got a negative leading coefficient because they have the wrong end behavior. Okay, cool. So that leaves us with 2 graphs to choose between, 1 and 3. And let me zoom in for this next part because, you know, I don't know about you, but without my glasses, I can't really see what I need to know to finish off this last part. Which one of these 2 or 3, is the correct
3.
answer? All right, Johan, 3. Why 3?
3 because our y-intercept is a positive number, and 2 has a y-intercept of a negative number.
Brilliant. Yep, exactly right. 2 has a negative y-intercept, 3 has a positive y-intercept. Our graph has to have a positive y-intercept. So eliminate number 3, or say number 2, because it has a negative x-intercept. Does anyone need to borrow a graphing calculator today? Because now is the time to get one. If you don't have one, so this next part is something for which you're going to need a graphing calculator, and I can't be more plain than this. I will expect something like this on an exam. Now, on the last exam, there were some people that struggled a little bit with one of the graphing calculator parts, so Hopefully that won't happen with this one. Hopefully you'll take my word at this. Let's see. So let's start by plugging in the correct polynomial, which is this one, into our graphing calculator. 1.2x to the 5th, etc. So let's go back and clear out all the stuff that's there. Clear and clear. So I want 1.2x raised to the 5th. Now when you raise it to the 5th, hit the right arrow to get out of the exponent before you start typing again, plus 3.75 x to the 4th, right arrow, minus 7x cubed, minus 15x squared, plus 18x. All right, so kind of a messy polynomial. Now, a good question is, well, what should I set my window to in order to graph this? So that's a good question. Do I need to think about this too much, though? Do I need to think really hard about what to set my window to? Well, not really, because I made a suggestion like right here. Hopefully you're familiar with that notation. That's my x min to x max, y min to y max. So we went from -5 to 3 on the x-axis. And I'll do 1 for x scale. And for y min, it was -75 to 75. Now I probably don't want to leave y scale as 50 because I'll just see one tick mark above and below the y-axis. So choose something like 10, 15, 25, something that is pretty reasonable. And you should get a graph that looks like this. Yay. All right.
Remember, I had a problem on the test. I was trying to get like a specific point, but it kept skipping past it.
Yes. Well, here, let me help you. So right now, what we're going to try and find are what are called local min and local maxes. So I want you to find a couple of these. So local maximums, maxima, and local minimum. So let's see if we can't find those. Now, some of you may have run into trouble because you use the trace key to try and find these points. We don't want to use the trace key. I mean, if you put a tracer on it, trace, yeah, you can come around and you can get kind of close to some of these values, but let's do better than just getting close to those values. Let's find the exact values. Now this point over here, let's see, around here, that's the biggest thing nearby. Is that the biggest y value for the graph overall?
No.
No, but locally in its neighborhood, it's the biggest value. So that's a local maximum. We want to find that local maximum. We're going to do that with the calculate menu. So you hit the second key, then calculate. Is there an option here that looks like it might be helpful? Yeah, the fourth one. So let's hit the fourth one. Now, when your calculator is looking for a maximum, it wants you to give it a window. It says, all right, tell me what the left bound is, what the right bound is, and I'll look in between there. So you've got to take your cursor and go to the left of your maximum. Doesn't matter exactly where. I can go a little bit farther, I can get a little bit closer, it doesn't matter. Just find something convenient and then press the enter key. It says, oh, okay, that's my left bound. Now tell me what the right bound is. Now you've got to move to the right of your maximum and press enter again. Now there used to be a time in which computers were a little bit weaker and processing power wasn't as great, that you needed to give it a good initial guess, but that time is long since gone. It's looking for an initial guess. If you wanted to be nice to your calculator, you could go close to it, but you don't have to. Just press enter one last time, and that'll tell you your maximum. Now in my case, Yeah, I'm getting negative 2.99998. Yeah, a lot of you probably got negative 3, and that's okay. Now, on the test, I could ask you for a couple things. I could ask you for where the maximum is, which would be either the x-coordinate or both of them, or what the maximum is. What the maximum is would be your y-coordinate. So let's just list both of them down. I'll probably also ask you to round it to the nearest thousandth place or something like that. So this point is really going to be negative 3 and 12.15. That's your local max. Max at x equal negative 3, y equals 12.15. Let's do it again and try and find the local min. That's going to be this point down here. By the way, how many other local min and local maxes do I have in this one?
2 maxes, 2 min.
Yeah, you've got 2 maxes here and here, and 2 mins here and here. So now there's a way you can kind of predict how many maxes and mins you could have. And it's kind of a nice, interesting relationship. So let's take a look at that for just a second. We have a 5th degree polynomial, and you have a total of 4 local mins and local maxes. How about down here in example G? This is a 3rd degree polynomial. How many local mins and local maxes do I have now?
2.
2.
Or 1 of each.
Yeah, you got 1 of each. So can you see a way you can predict how many local mins and maxes you could have? We had a 5th degree polynomial here, 4 local mins and maxes. 3rd degree polynomial here, 2 local mins and 2 local mins and maxes. It's going to be 1 less than this degree here is what you're going to end up with. The number of possible local mins and local maxes. Let's go back and finish this up by finding 1 more of these. Let's find a local min this time. So I'll hit the second key and then the trace key. I want a local minimum. That's 3. Let's zoom over a little bit closer to this. I'll press enter here. Enter here. I'm not going to give it an initial guess. I'll just let it ride as is. So negative 1.414, 216, etc. Most of you don't recognize it, but I'll tell you that's the square root of 2. That's all right. You don't need to recognize it. So local min at x equal negative 1.414. Y equals, I didn't catch the y value. What was that y value? Let me look back here. Negative 27.445. Nice. Are you comfortable with finding local mins and local maxes using your calculator? It's not enough just to hit the trace key. You've got to find it with that calculate menu. This is a nice trick for you when you get into your calculus classes. You're going to be finding these local mins and local maxes all the time. They're going to tell you a lot more about your functions than I can tell you here. All right, let's roll on.
Do we write the local minimum and local maximum, like, do we write them as like coordinates?
So it's going to depend on what I ask. If I ask, for the x value or where it is, you can give me the x value. If I ask what it is, you can give me the y value. Or maybe I'll ask for both of them. So just pay attention to how I word it on the test, because I will ask for what I want.
Okay.
So, these are really good. And I'll do the first one with you, and I want you to do the second one with you, or do the second one on your own, or maybe with your neighbor. But here's how this would look. Suppose I asked you to find, what function this polynomial could be. I guess the first thing I would notice is the end behavior. Which of our 4 end behaviors is this one? D. So that means we expect an even degree polynomial with a negative leading coefficient. Okay, so let's take a look here. X, let's see, I don't want to write X, I just want to write the root. Let's take a look at the roots. What are the roots of this polynomial?
-3, 0, and
Perfect. -3, 0, and 2.
-3, 2.
So next thing I want to look at is the behavior. What kind of behavior, Dalen, am I getting at the root of x equal -3?
It's bouncing off. Did you ask me?
Oh, I said Dalen, my bad. They're too close. Yeah, it's all right.
I knew I was
All
gonna
right.
go one point semester. It's bouncing off.
She's got you. She's got your back on this one. This one's a bounce. All right, so Dalen with a D. What happens at x equals 0? What kind of behavior is that?
Right.
All right, so straight through, perfect. And let's see. Angel, how about x equal 2? What do you think is happening here? Good, so that's a wiggle. Now let's see if we can't come up with some multiplicity.
a quick question.
Yeah, please.
At 2, if it touches it at all like that on the test, you just say that it's a root, because it kind of looks like it's along that line, if that makes sense. It doesn't like it crosses just straight at 2.
Well, see what happens at the root here and why it's a bounce is because it starts out on the negative side of the x-axis, it touches here, and then it continues on the negative side of the x-axis. It doesn't cross through, so that's what makes it a bounce. Whereas opposed to this one, you start on the negative side of the x-axis, to the left of x equals 0. To the right of x equals 0, the graph is above the x-axis, so that one went straight through. This one kind of, thinks about it for a little bit, comes in shallow, and then eventually says, okay, I'll change.
So
But it's not going straight through.
So if it looks like it's kind of hugging like that,
That's just because of the resolution of my graph. It's really only just touching it for an instant and then coming off.
okay.
How about the multiplicities here? What do we got for multiplicities? Ace, want to deal with multiplicities here? Bang those out. So at -3, what is the multiplicity associated with a bounce?
2.
2. Now you could use 4 or 8 or whatever, but let's just go with the lowest one that we can, which is a 2. Straight through, there's only one choice, right?
Yeah.
A 1. How about a wiggle? 3. So overall, we got a degree of 6. Well, that's promising because we knew we had an end behavior of D. And D at least has an odd degree. Let's take a look at the binomial terms that we associate with this. Now, if I have x equal a root at -3, then what's going to be my binomial term? X plus 3, just an x, and an x minus 2. These are the terms that we're going to use to put together our polynomial. So our polynomial, p of x, is going to be x plus 3, and then an x, and then an x minus 2. but I've got to do a couple things, starting with the degrees. The degree of this one has to be a squared, because that one was a bounce. What's the degree of x?
1.
1. And the degree of x minus 2? 3. That's just coming from the multiplicity that we figured out by looking at the behavior of the function here. There's one more thing that's missing in order to get this one right. Ah, well done. It's not really written anywhere, but because the end behavior is down, you have to have a negative leading coefficient. So we'll just put a negative out front, leading coefficient. Perfect. And leave it factored here. Now, if you prefer, I mean, aesthetically, I guess I kind of like the x out in front, negative x times x plus 3 squared times x minus 2 cubed. That's fine as well. I don't care. There's 6 different orders you could write these things in. I'm not really going to grade you on that. All I'm looking for is that you have the correct binomial terms there.
That's
And to the right degree. What's that?
Amazing how it all comes together just from looking at it. I would've
Oh, yeah. And
never
then
thought.
how could you double check yourself if you wanted to? If you're looking at it, like, oh man, this is an 8-point question, I better get it right. How would you double check it?
You start from you do everything the opposite way, so you look at your last binomial terms and check it.
Probably an easier way than that. I mean, that's a good way, but Lucas?
Put it in your calculator.
Yeah, put it in your calculator. Now, your instructor is smart and occasionally malicious. I might not give you a scale here on the y-axis, so you might have to figure something out, but I actually have to give you the scale on the x-axis, so I can't really trick you too much. But yeah, you could reverse engineer it based on what you see here and make sure it matches up here, or you can put it in your graphing calculator. I am not going to take your graphing calculators away from you on the exam. Please take the time to double check these and get them right. Your turn. And if you're watching this at home, you can pause the video, try and come up with this polynomial. I would work it the same way we did the last one. That is by figuring out the roots, behavior, multiplicity, etc., and work from there. Okay, so Arden, we've got roots here at -1 and 2. So let's put those in. What's the behavior of the function of the polynomial at these 2 roots? What do you see?
At -1, like I put wiggle and then, or 2 bounce.
Good, a wiggle and a bounce. Nice.
I thought it
Wait.
-1 would be
Oh.
That's not a straight through.
No.
Straight through would look like this, where it just
Talk about -2.
Rips right through the x-axis without
Talk about 2.
pause.
Not 4.
Or maybe I misunderstood you.
I thought -1 was just straight through.
No, it kind of curves into the x-axis. Doesn't go straight through. Straight through, for contrast, would be this one at x equals 0. That went straight through.
Oh, so
It doesn't pause at all. Over here at x equal 2, the function kind of snakes its way through there. It doesn't just go crashing through. It kind of skirts the x-axis for a little bit. It changes its contour. It's concave up and then concave down. But in the middle, it crosses through there at 0 through a wiggle.
So it's only straight through on 0.
So the only example that you have of straight through is at 0
It's
here.
at 0. Okay.
Yeah. So what are the multiplicities associated with each of these? A wiggle's a 3, a bounce is a 2. What's the degree that we're working with?
5.
All right, degree equals 5. Now, if you look at their end behaviors,
Are we just leaving 0 out of the picture? Where it intersects with the y with the y.
that's not a root though. In the last problem, x equals 0 was a root. Here, x equals 0 is not a root. The graph doesn't cross the x-axis at 0. So it has a y-intercept.
It has to. Yeah, talk about the y end. That's why.
Yeah, we're not worried about the y-intercept. We can look at the y-intercept in a minute just to double check ourselves. But for right now, let's look at the binomials that you associate with this. What binomial terms do you associate with each of these?
X minus 1, x plus 2.
X plus 1
X plus 1,
and x minus.
x minus 2. Notice that those signs are changing when you go from the root to the binomial. This end behavior would be end behavior A. So end behavior A means you've got a positive leading coefficient, so we don't have to worry about the negative like I did with the previous one. That's going to be P of x is going to be x plus 1 times x minus 2. And now I need to throw in some exponents here. Exponent for the x plus 1 term is coming from the wiggle, which is a 3. And x minus 2 has a bounce, so that's going to be a 2 here. And that's it. That's our polynomial.
What if you didn't want to do the smallest exponent?
I mean, look, I would have to accept if you did a 5 or a 6 or an 8 or a 7, these other ones here. But I always suggest you just go with the lowest one. The benefit is that that's probably what your instructor is going to use. And somebody mentioned the y-axis. How do I find the y-intercept of a graph? Set x equal to 0. What if I set x equal to 0? I get a 1 here, cubed is still 1. 0 minus 2 is negative 2. What's negative 2 squared? 4. Take a look at your graph. Right there at 4. P of 0 equals 4. 0, 4.
Oh,
So that's kind of nice because that's reassuring that, yeah, we got it. Now, we didn't have to deal with x equals 0 explicitly because it wasn't one of our roots.
if we,
But it's nice that you can check it that way.
if we did it to any other degree, would it still be 0?
If you used other degrees than this, it wouldn't match the 0. It'd still have similar behavior here and here, but it wouldn't match the root there.
Okay.
Johan?
Wouldn't we need to put a negative sign on the left side of x plus 1?
No. Let's take a look at what would happen if you put a negative sign on the left side of x plus
I
1.
think, looking back to the last example where we put a.
Yeah. Let me get rid of a couple things here. I don't know if I have that one programmed in here. No. Well, let's just check it out. If I do P of x, P of x equals x plus 1 cubed times x minus 2 squared. That's looking pretty good. But what if I put a negative out in front like you suggested?
We give reflect.
It's going to reflect it. So it's going to open the other way. This would give you end behavior B, where you're going up to the left and down to the right. So it would give you exactly the wrong part here. So this negative sign out in front, getting that correct, that's a point or two, depending on the problem. Yes?
On the test, do we have to memorize all the different behaviors or?
You should probably memorize those as you do the homework. And I will ask for bounce, wiggle, and straight through. So I guess the answer is yes. You are going to be responsible for knowing those types of behaviors by name. But if you're doing even a modest amount of homework, I think that you'll have those memorized without making a conscious effort to, write yourself some flashcards. Okay. Anything else on that one? Yay. Let's put this one in the book.